mechanism. Whenever you see a volcano erupting, the big billowing cloud, of course, a lot of it's ash, I understand that, but a lot of that is just simply condensed water vapor or steam. The main gas evolved from all volcanic eruptions is water vapor. So all magmas contain water. Well, think about that now. Here's this magma. Water's dissolved in the magma. Kind of hard to visualize, but it is. And now what we're going to do, we're going to cool this magma down, and we're going to start precipitating out whatever minerals that magma is allowed to precipitate. In other words, again, whether it's felsic or mafic or whatever. But the point is, if you look at the minerals in Bowen's reaction series, or that crystallization series, and look for things that are dot waters, you won't find any. Okay, so we don't have to worry about those kind of minerals. Are there any minerals in the series of silicate minerals that have hydroxyls? Yeah, there are a few, but the hydroxyl, if you look at the entire formula, really doesn't seem to be very, very important. There are other things that are more abundant than hydroxyl. So the point is, some water is used to create minerals like the micas or like hornblende, but not much, which means that as these minerals start to precipitate out now, they're not needing to use that water. So the water in the magma becomes more and more concentrated. And pretty soon you're going to get to the point at the very end of crystallization when it's almost all solidified. What was once a molten rock mass with water dissolved in it is now going to be mainly just hot water with whatever's left dissolved in it. But that's the point. What's left? Well, let's think about that. What could be left? Maybe gold. Look at the minerals in Bowen's series. Do any of those silicate minerals require gold? No. How about silver? No. How about platinum? No. How about a lot of metals like that? No. You see, they don't need them. They don't want that stuff. So what happens? It's now in that solution at the very end. So we have this hydrothermal solution, we call it, just perhaps chock full of all these kinds of what we consider very valuable, rich, and expensive elements. Then what happens? At the very, very end, that stuff is shot out into the host rock, the stuff that's been contact metamorphosed, you see, and is shot out there in cricks and crevices and like that, and all those things start precipitating out. And the result is perhaps a little vein of gold, a little vein of silver, deposits of metals that now are economically of value, and as a result, those are sites where we go to find that stuff. So note, one of the important things about this hydrothermal metamorphism is that as a result of it, we are creating, in many respects, a lot of metallic deposits of all kinds of things, molybdenum, you name it, that are being formed as a result of the end product of crystallization of magmas where these very rich and valuable things are concentrated in the final hydrothermal solution. It's all part of hydrothermal metamorphism. But again, note, then the metamorphic rocks we're talking about, now these things are different in composition from what we started off with. So anyway, you can get some feeling that, I hope, from just that little discussion of what the range of metamorphic conditions are and the kinds of different kind of metamorphic rocks you can find. It's very, very, very complicated. Now, the last thing I want to talk about actually has to do with how we describe metamorphic rocks. Metamorphic rocks are described as either being foliated or non-foliated. Now, here's the big difference between what foliation means. Foliation means that this rock contains platy minerals. Now, what's a platy mineral? Well, think back to our discussion of the silicate structures, those sheet structures where you arrange things, the silica tetrahedra, in sheets, and then sort of made sandwiches with the sandwich material being other cations, and then you stack them on top of each other to form things like mica and things like that. That would be a platy mineral, okay? Those are platy minerals. If you take a rock that has lots of platy minerals, and they're all aligned with each other, just picture this now. Between those sheets is sort of weaker bonding, so you could break it between there. Remember? Mineral cleavage. So mineral cleavage, that's why you could take those books apart of mica. All right, so here we have a rock that has platy minerals in it. All of them are aligned, and so it would break along those weaknesses. And so that would be what we refer to as foliation. So foliation refers to the ability to break along these planes of weakness. Well, let's just show you the different kinds of foliation. And again, let me start off my old favorite, shale. All right, we take shale, and what shale is are clay minerals. And remember now, they are sheet silicates. So when that shale first formed, what happened is all those little silicate minerals fell down. They're all parallel to each other in the individual layers of the shale. And then what we're going to do now is we're going to metamorphose this thing. And here's what we're going to do. We're going to say just under pressure. Okay? So here we take this shale now, and we're going to set it under pressure. And under the new pressure now, those clay minerals aren't very stable, and what they're going to start doing is they're going to start changing, recrystallizing into, let's say, mica, okay? Now, here's the point. Let's say, for example, here was the pressure, your 2 fingers. And as these new platy minerals formed, what they're going to do, they're going to reorient themselves in such a way that they are stable under those new pressure conditions. So here's what I want you to picture in your mind. Take a coin, and what I want you to do is to hold this coin between your 2 fingers, like that, and you can hold it any way you want, but press on it as hard as you can, okay? Question, what would be the stable position, do you think? For example, if you took the coin and you put the coin like this, okay, and you're pressing on it, how stable do you think that would be? Just try it. You press on it harder and harder, pretty soon it's going to flip out. That's all there is to it. It's not a stable condition. On the other hand, if you took the coin and you turned it sideways like that, and remember now, your fingers are directly opposite each other, that's called non-rotational compression. Now you can push as hard as you want, and it will do anything because it's in a stable position. So note now, all these new platy minerals that are being created out of the clay minerals, now what they are, the micas, they're all rotating, getting an order, so they're all perpendicular to the forces that created them. Now we have, instead of clay minerals, now we have mica and quartz, all right? Well, it's a new rock. What do we call it? We call it slate. That's what slate is. Basically, slate is a metamorphosed shale. Now, the thing about that, we call that slaty cleavage. Why? Because if you take just a wedge of some kind of chisel, you can break that off into sheets, very uniform in thickness, very smooth surface. That's slaty cleavage. For example, back before the days of the whiteboard and the green board and the orange board, we used to have blackboards. That was slate. Now, I think they actually sort of polished those surfaces to get them really fine. But I remember being on a field trip over in Wales and going into a quarry where they were actually making slates for roofs. And these guys were just sitting there with a chisel and hammer and splitting off these slabs that were perfectly uniform, about 1/4 of an inch thick, beautifully smooth on one side. That's what's characteristic of slaty cleavage. Now, if we squoze a little bit more, I love that word, squoze. Can I use that? Fair enough. If you squeeze a little bit more, now the mica is no longer stable. It's probably going to change to something else, maybe chloride, but other things are going to start happening. For example, there's going to start reactions now, and then they're going to be equidimensional crystals formed, not platy minerals, maybe things like garnet. And now, for example, in between these sheets now, there are going to be places, there are going to be garnets in here. So now if you try to split it, it'll split into layers all right, but they won't be uniform in thickness, and they'll be a little rougher and not quite as smooth. Well, we call that phylitic cleavage. Phylitic because the rock now is a phyllite. Note that a little bit change in composition. Now we have a phyllite. Now, if you keep the squeezing going on, pretty soon you start making more and more and more of those non-platy minerals, like, for example, garnets. And pretty soon, if you try to split it, it won't split in layers. What happens, it splits around the individual garnets, and you get flakes and things like that. Well, now we call this schistose cleavage because the rock is called a schist. The last of the kind of foliated rocks, and this isn't, there's no cleavage involved here. I don't really know why it's called a foliated rock. It's called gneissic banding. The rock is called gneiss. Gneiss is the most abundant of all the sedimentary, of all the metamorphic rocks. Now here's what it looks like. It's banded. Dark minerals, light minerals, dark minerals, light minerals. Now, you tell me how the dark and light minerals separated from each other as a result of that metamorphism. I really don't know. But that's called gneissic banding. Now, so those are the foliated rocks. Now, the non-foliated, very simple. Non-foliated rocks would be rocks that have no platy minerals whatsoever. Case in point, a limestone. Let's say you take a limestone, and now you're going to metamorphose it. What happens is it simply recrystallizes from the individual little crystals of calcium carbonate, whether they're individual crystals or maybe shell fragments, and they're going to recrystallize into new crystals. Shell fragments are gone now. You've eliminated all the fossils. They're gone. And what you end up with is a new rock where you have these relative uniform sized crystals of calcium carbonate all locked together. And the new rock, of course, no foliation whatsoever, and the new rock is called marble. That's what marble is. It's simply metamorphosed limestone. And the beauty of marble is you want a marble that's most uniform in texture. You don't want weakness, because if you're a sculptor and you start whacking away at this time to carve something, you don't want to run into a plane of weakness that's going to break and an arm will fall off or something like that. So anyway, that's marble. That would be a classic example then of a non-foliated rock. Okay, so much for metamorphic rocks. Next on to volcanoes.